Hello, everyone. Happy Monday. Hope everyone had a good weekend. And we're going to get going here on section 1.2. So I'm going to go in today, you guys, and check the past week. I'll take attendance based on interacting with the material, and then I will get these notes done and posted, and you can get going. Okay, so what we're going to do today is we're going to talk about different graphs. So we did some bar graphs before. We did some side by side bar graphs. None of those are official statistics graphs. This is kind of the first official statistics graph you guys will see, which is real simple. It's just called a dot plot. It literally is exactly that. You go down and you create a simple number line and you put dots above the value for the data that you're looking at. Okay, so this first example talks about two people, Brian and Jessica. They decided to move and are considering 7 different cities. The dot plots below show the daily high temperatures in June, July, and August for each of these cities. Help them pick a city by answering the questions below. Okay, so again, the dots represent the daily high temperatures in June, July, and August. Okay, so as you go through here, for instance, this dot right down here is talking about city G, and it's above, it looks to be about 2, 4, 6, 8, so right around 58 degrees. So that one dot is representative of 58. Okay, so what we're going to do at the beginning is just talk about clearly the data for these different cities are all different. And part of statistics is being able to describe the data that you see. And we do that in particular ways that we'll get to on page 2 of the notes. Okay, so the first one, what is the most important difference between cities A, B, and C? So this isn't anything official. This is just you looking at cities A and B and C. Well, to me, if you can trace this invisible line over these, okay, that would be the description of the shape. So all of these seem to have similar shape, right? They all have this single peak here, right? And so what's the main difference? Well, the main difference would be like the center, right? The center of this distribution. The distribution is all of the dots combined. The centers seem to be different, right? For instance, in city A, the center of this distribution seems to be right around, if I scroll down here, right around 90 degrees. So it's clearly hot in city A. In city B, the center would be down here around 70, and the center here would be right around 80. And so the main difference between cities A, B, and C is they all seem to have different centers of their distribution. And so I use this word center, right? But that's not something that you guys would probably use. You guys might have heard things like the word mean or median. Those are typical math things that you learn in middle school, and then they come back again around SAT time. So mean is a fancy word for average, and median is the middle 50% of the data. So this word center takes care of both of those. So it's saying the average or the median is somewhere around there. Okay, so it's just a more generic term. Okay, moving on to number 2, what's the most important difference between C and D? Well, C and D, here, you can see that the distribution, if I draw this fancy line over the top, just I'm kind of eyeballing it, there's clearly a difference, right? And what is the difference? How do you describe this data compared to this data? Well, we use a word called spread, right? This data is more spread out. You might have heard another word from the past called range. Range is how far it is from the lowest to the highest. So the range of this data would be bigger than this one. Okay, so we're just going to use the generic term spread. So you would say D, city D, has data that is more spread out. So, I forgot an R there. Let's do that. So it's more spread out. And so now we've talked about center, we've talked about spread. Okay. And then moving on to 3, what are two important differences between D and E? Well, look at D and E. Definitely the spread, right? Look at this. This is all kind of compact right around here, right? And this is much more spread out. So one difference would be that D, city D, is more spread out. And what else is different? Well, look at these two little points. These are really, really far away from the rest of the data. And so these guys here, we would call possible outliers. So outliers are points that don't seem to match the rest of the data. So either, right, one of two things happened. Either there was this random, ridiculous day where it was 104 degrees, right, which actually happened, or there was an error with the instrument, right? Maybe something happened and the temperature gauge was off that day. So we don't know, but what we do know is that city E appears to have possible outliers. Okay, so another fancy stats word. So we've talked about the center of distributions. Again, what's a distribution? A distribution is a collection of data points that have been graphed. And what we're doing is we're describing it. So we've talked about the center. We've talked about how spread out they can be. We've talked about outliers. And now this last one here, what is the most important difference between C, F, and G? Well, if you come here to C, right, nice smooth curve, single peak. Then we've got F. We've got this different situation here where you've got a peak on the left and then this slow kind of slope out to the right. And then G, you've got a peak on the right and then this slow kind of slope to the left. Okay, so definitely the shape of all three are different. And these are actually things, right? This is called roughly symmetric. You guys know symmetric, right, from geometry? It's just like if you fold your paper in half. We use the word roughly because it's statistics, it's real world data. Nothing's going to be perfectly symmetric, but this looks to be roughly symmetric. This guy and this guy on the next page, we'll actually define them as skewed, right? S-K-E-W-E-D. So skewed. This guy we consider skewed right, and this guy would be skewed left. And again, I'll give you a definition on the next page. Okay, so at the top of the next page, we're just going to do a dot plot, right? You guys should be able to perform a simple a number line with the dots above it. The way that I do this, if you're going to make a dot plot, is I look through the data and I try to find the smallest number. Looks like 570 might be the smallest. And then what's the biggest number you can find? Well, there was 870. I don't think there's anything above 870. And so the reason I do that is so I can get an idea in my brain, like what should the left side of my graph be and what should the right. So it seems like if I go from like 550 to 900, that should be okay. So if I start down here at 550 and I'll do 60, 70, 80, 90, 600, 610, 20, 30, 40, 50, 60, 70, 80, 90, 700. So this was 1, 2, 3, 4. This is 650. And then 10, 20, 30, 40, 50, 60, 70, 80, 90, 800. And then 10, 20, 30, 40, 50, 60, 70. That's going to be the max out there. And you guys could have chosen to do a different way, right? You could have started down here at 500 and done less tick marks, right? You could have counted by 20s. It's up to you. You just have to create a consistent number line. And then all you do is you go put in your dots. So that dot 570 should be right above the line, which is 570. Okay. And cross them out as you go. So then it looks like we have a 580 dot. And then we've got a 740. So I guess there's no reason we can't just go along here. 850. 850. So this is the first time we have a repeated number. So if you have a repeated number, right, you've put in your dots down, it's important that your repeated number goes directly above the other dots so that you can start to see height, right, so that we can calculate that. And then we've got an 870, and then another 850, and a 670, another 670, 630, 690, 780, 610, 790, 700, and 640. And so you guys can start to see that that's nothing really interesting. I mean, it seems really spread out based on the graph that we did. It's all correct. But I think the one takeaway from this, you guys, is having 1, 2, 3, 4, 5, 6, 7, 8. Having 16 data points in statistics is pretty terrible, right? We're talking about Consumer Reports rating frozen pizzas. Here are the amounts of sodium, right, in a single serving of 16 different brands of cheese pizza. Well, when you only have 16 different data points, you don't really get a feel for what's happening, right? You can say some generic things about it, but it's nothing too interesting. Okay, so when you are asked to describe data in this class, you don't have a choice. You need to use this acronym SOCS. It's not spelled correctly. It's just SOCS. And this S stands for, we're going to say spread. This O stands for outliers. This C stands for center. And this S stands for spread and what am I missing here? Shape. Okay, so you must, when you describe, data for this class, in order to get credit, you must address all 4 of them. Even if there are no outliers, you have to address the fact that there could be, or you simply say there does not appear to be outliers. Okay, we don't really know for sure what an outlier is. We would just say it's those points that are really far away from the data. Okay. All right, so you must address these 4. Okay, so how do you address shape? Well, we talked about this symmetric. So symmetric would just be a nice smooth curve, right, with a single peak. Skewed right has a peak and it goes out to the right. And skewed left has a peak over here and goes out to the left. Okay, and some people remember skewed, kind of sounds like skied, you snow ski. You would not choose to ski to the left because you would die, right? You'd fall straight down a cliff. So you would choose to ski right. So skewed right would be this way. Skewed left, if you decide which way to ski down the mountain, you don't ski to the right, that's falling off a cliff. You ski to the left, so that's called skewed left. Okay. Unimodal means one peak. You guys can hear my daughter's parakeet in the background. Sorry about that. So one peak. And then bimodal would be 2 peaks. So you can think of it like this. And then uniform would be just flat. And those are words that we would use to describe, right, shape and distribution. Okay, so let's go to the last page here and kind of pull it all together. And this last page talks about top versus bottom freezers, right? Seems like a silly thing, but once you switch from a top freezer to a bottom freezer, for me, it's way better because you spend most of the time in the fridge. So it's nice that your fridge is up top. So what they're doing here is they're comparing them. They give you some data about how do energy costs compare for refrigerators with top freezers and with bottom freezers. Okay. The data below are from May 2010 of Consumer Reports. So compare, right? It says to compare the distributions of energy costs for the 2 refrigerators. You do not have an option here. You can't, even though you guys are, a lot of you probably are really good English people and you could write a lot of good sentences about it and say good things, you must check your SOCS, S-O-C-S. Okay, so use your acronym. We're going to first talk about spread. It doesn't matter the order, you guys. You could have done shape for S instead of spread. And all you want to do is you want to use comparison words to compare the difference. Well, what's obviously different about bottom freezers versus top? You would say bottom freezers have data that is much more spread out than top freezers. So you must address the spread of the 2 data sets, and you're comparing them, right? Don't just say the spread of the bottom is this and the top is this. You want to compare them. So we said bottom freezers have data that is much more spread out than top freezers. Well, contextualizing that just means that the range of energy costs varies much more on bottom freezers than top. You can pretty much guess what your annual energy cost is going to be if you have a top freezer. If you get a bottom freezer, right, you have no idea what you could get. It could be super cheap or it could be super expensive. Okay, outliers. All we're doing, you guys, is addressing, could there be outliers? We don't know. I haven't given you an official way to find them yet, but these two look pretty far away, right? Far away from the collection of data points for the rest of the bottom freezers. Okay, so we would say it appears that bottom freezers have two possible outliers in the data. Okay, and then we're going to talk about center. So we're going to address the center. You're just kind of eyeballing it at this point, you guys. You don't really know. So the center of this data, right, it seems to be right around there, right around 70. So we would say the center of bottom freezers looks to be about, we're just estimating, which is totally fine, 70, okay, which is higher, right? Comparison words, you guys, don't just give me the data, compare them, which is higher than top, which is about, and let's look up here, right? The top seems to be right around 56. Okay, so what I don't want, it sounds simple, but this is the big mistake here. I do not want you guys to say the center of the bottom looks to be 70, the center of the top looks to be 56. That is just reporting data. That's not using comparison words, right? That's a big thing. So you want to say, right, this is your comparison word there, that the center of the bottom freezers is higher. Okay, our last one here would be shape. And we would say, this guy, you know, how do you describe shape? Well, you want to draw that invisible thing over it, and then it goes way out to the right. And then here, right, it's just kind of compact. I kind of feel like, you guys, if you take away those possible outliers, this looks roughly symmetric, right? So I would say both are roughly symmetric, obviously with bottom having those two outliers. So both top and bottom seem to be roughly, right? Just estimated, seem to be roughly symmetric. And this would be ignoring the two possible outliers on bottom. Okay, so what happens if you didn't think? What happens if you thought, hey, look, if I don't ignore these, this thing could be considered skewed to the right because it's got this long tail? Absolutely, right? So sometimes we will disagree on the shape. That's okay. You're just addressing what you see in your mind. Most of the time on an assessment, it would be very obvious that it would be skewed to the right. You'd have data that looks like this, right? Lots here, and then the slow tail to the right. Okay, so we have learned about our SOCs. That is the only way that you guys are allowed to describe data or compare data. You must use the acronym SOCs. All right, guys, take care.